Okay, starting on Chapter 9, Section 6, and these are the ratio and root tests. We're actually going to first, we're going to do problems 5 through 10, which are kind of a summary of what we've been doing so far and trying to match them up to the graphs. So let's just write out what they are, and then we'll try to think about what's going on with each one of these series. And what we're going to be looking at is the partial sums. So we take the first term and then we add the first and second terms. Look at that. And you can see we have a couple that are alternating series. Okay, so let's look at the graphs. We see A starts at 2, B starts at 2, 3 starts at 3/4, D starts with, looks like 3/4, E starts at 4, and F starts with 9, but it bounces around. So it looks like we have two alternating series. So let's find ones that look like there is some alternating nature to them. So these are the two alternating series. So it looks like not E, but F is one of them. And it actually doesn't look like any of the other ones. So the question is, what is going on here? Because these two here are alternating series. This is -3 to the n plus 1 power. So at least we should be able to figure out which F is. It starts at a 9. So you can see when n equals 1, we get 3, 1 plus 1, which is 2, and we have -3 squared, which is 9, divided by 1 factorial, which is 1. So 7 appears that it has to be F from that fact. Okay, so let's look at this one, see what's going on. So let me add a page so we can maybe just do a couple of values of n and see what happens. So we have n, we have a sub n, and then we have this partial sum. S sub n. So number 8, we start with 1. So we'll have -1 to the 0 power, which is 1. And then we have 4 over 2 factorial. 2 times 1 is 2. 2 factorial is 2. 2 divided by 2 is 2. So a sub n, a sub 1 is 2. So the sum starts out at 2. Okay, the next one, probably what happens is the reason this doesn't become negative is because the second term is fairly small. So you can see when n equals 2, we get 2 minus 1, which is 1. -1 to the 1 power is -1. Then we have 4 divided by 2, 2 times 2, n is 2. So we get 2 times 2 is 4. 4 factorial is 4 times 3 times 2 times 1, that's 24. So we get 4 over 24, so this is 1/6. Okay, so what I did was I took n equals 2, and I got this, and this becomes negative. This is 4, and then I have 4 factorial, which is 24. So I get negative 4 over 24, which is negative 1/8. Actually, is it 1/8? 1/6, negative 1/6. So it's actually negative 1/6, so when I add these two together, I get 1 and 5/6. So there is one, which is B, that has very slight alternating behavior. But the thing to remember is that it doesn't have to go plus or minus as far as the value, it just has to alternate between some final value. So I'm pretty sure about that one. Okay, so we've gotten those two done. So what do we have left? We have A and E, which one starts with 4 and one starts with 2. So we probably can tell which ones those are. So when n equals 0 for this one, so if we look at 10, which is summation from n equals 0 to infinity of 4 times e to the minus n. So we'll make a little table up here again. So we have n, we have a sub n, we have the partial sum. So n equals 0, a sub n is 4 times e to the 0, which is e to the 0 is 1, so you get 4. So the sum is 4. Then we do n equals 1, you get 4 times e to the minus 1 power, e to the negative n. So that's 1 over e. So that's going to be approximately 1 to 2 or something like that. So this is going to be 5 something. So if we look at e, we see that that matches up well with e. And there's no other one that starts out at 4. So that's good. Okay. We've already found the other one that starts at 2, which is an alternating series. So that leaves A as the other one that starts with 2. So we look through here. If you let n equal 1, you'll get 4 times 1 divided by 5 times 1. So that's 5 minus 3, which is 2. So you get 4 divided by 2, which is 2. 2 to the first power is 2. So number 9 starts out at 2. And the only other one that we have left that fits that bill is A. So we picked E because it started at 4. We picked A because it started at 2, but we'd already figured out the other one that started at 2, which is the alternating series. So now we're left with these two, which it looks like this one should increase much more slowly than this one because they're both 3/4 the n, but here you're dividing by n factorial. So this, the second, third, fourth, fifth terms, this whole thing, a sub 2, 3, 4, 5, are going to get much smaller, and so it should level out much more quickly. So the two we have left are D and, let's see, D and C. So you can see, and they both start at, when n equals 1, you get 3/4. So they both start at 3/4, but you can see that D takes much longer to level out. So that would go along with this one. So this is D, and then that therefore leaves this one as C as the choices. So I don't have to necessarily plot the whole thing. I can use logic to figure out which ones are which and use process of elimination as I went along. So let's kind of review what I did. There were two alternating series. This one, when n equals 1, I got 9, and so there's only one alternating series that started out at 9, which is F. The alternating series, which decreased very quickly, was B. So it starts at 2 and it just dips below, the second point just dips below the final value that it reaches. So I got that one. Then I had these two started with, this one started with 4, and there was only one that started at 4. This one started at 2. Two of them started at 2, but this was the only one that was left over. These both started 3/4, but this one decreased. The nth term decreased much more rapidly, so it should come up and level out pretty quickly, whereas this one is multiplied by n instead of dividing by n factorial. So this one levels out much more slowly. So that's the logic I used. And since I do have my solution manual, I will just double check. Pretty sure I'm right. If I'm not, I'm in trouble. Okay, so 5 is D, 6 is C, 7 is F, 8 is B, 9 is A, 10 is E. There we go. I'm trying to see what the book does. Yeah, they do the first couple of terms. They look at the first and second terms. That's about it. Okay, so the next group of problems involved a ratio test. So if you're looking at your book, you'll see that typically they are ratios of two types of functions. They can be factorial, they can be exponential, they can be like a geometric exponential type thing. They can just be polynomials, single terms of polynomials. So that's kind of the way it works. Looking at all of those, they look like ratio tests. Now, when we get to 33 to 36, you'll see the P-series doesn't look like a ratio. So those are probably fairly simple. So that's kind of what I would look for if we had a set of equations which we didn't know which test to use. It's a ratio of two different kinds of functions. And we said what we're going to do. What did we say we're going to do here? Find my list of problems. And it's somewhere around here. Oh, here it is. So we're going to do 13 first. There's probably a lot of functions that can use the ratio test, even the ones that we've done before using other tests. Some of the earlier tests are easier to do, so this might be a choice of last resort if you haven't figured out another way of doing it. Okay, so here we go. So what you do is you write down a sub n, which is the term in this summation. And then you do a sub n plus 1. So what we do is we substitute for n, we put in n plus 1. And the ratio test says we want to take the limit as n goes to infinity of the ratio of the absolute value of a sub n plus 1 divided by a sub n. And then typically we will, because we start with a ratio, to actually do the calculation, we take the reciprocal of the denominator and multiply it out. And what that results in is these ratios of similar type functions. So we know how to use the properties of exponents. We also know how to simplify ratios of factorials. So the next thing we do before we apply the limit is we simplify. So n plus 1 factorial divided by n factorial is just n plus 1. Because this is n plus 1 factorial is, let me just write it out over here, n plus 1 factorial is n plus 1 times n factorial. So we have n factorial divided by n factorial, which just leaves n plus 1. Here we have 3 to the n divided by 3 to the n plus 1. So that leaves 3 to the first power. So I cancel out one of those. Well, those, adding exponents, subtracting exponents. So I'm going to have 3 to the n minus n plus 1, the quantity n plus 1. When I do that, then that leaves 3 to the negative 1, and you bring that back to the denominator. It's 3 to the 1. So it's just 3. So in this case, if you let n go to infinity, for this case, this goes to infinity. And the ratio test says this has to equal, it has to be less than 1 for this thing to converge. So since the limit as n goes to infinity of the ratio of a sub n plus 1 over a sub n equals infinity, which is not less than 1, the series that we were given originally diverges. So let's just check that. 13 diverges. Oh, and I did that right. Okay. Okay, let's go to the next one, which would be 16. Actually, that looks familiar. I think I assigned that. So let me pick another one. 16, 17, 18. What I need to do is look at the handout I gave you guys today and see if I can figure out. Let me pause for a second. I don't want to be redoing ones that we're doing in class. Okay, we actually assigned 15 in class, so we can do 16. So we have n times 3 halves, and in this case actually it's not a ratio, it's a multiplication of two different types of functions, but we'll let a sub n be this. So a sub n plus 1 is n plus 1 times 3 halves to the n plus 1. So the ratio says we take the limit as n goes to infinity of the ratio of a sub n plus 1 divided by a sub n find out what that is. It's got to be less than 1 for this thing to converge. So what's the simplification we can do? Well, we can't do anything with just the linear terms. And that the limit of that part when n goes to infinity is going to be 1. So we end up with 3 halves to the 1 power. So 3 halves to the n plus 1 divided by 3 halves to the n. You take this and subtract that, you get n minus n. So you're just left with 1. So the first part of the limit is 1 when n goes to infinity, and the second part is 3 halves. So the answer is 3 halves. So since 3 halves is greater than 1, the series diverges. So we look at the handout, ratio test. If the absolute value of the limit is greater than 1, so since this is greater than 1, this diverges. And we check our answer. And that's what this is. Okay, let's do one more until we do a new recording. So this one's going to be, I think it was 19, but let me make sure I'm not repeating something here. a handout. So 2 to the n over n squared. I don't remember that one. No, I did 18. So good. So I did 19. Again, we have a ratio of two different kinds of function: polynomial, single-term polynomial, quadratic term, and a exponential term. So a sub n is 2 to the n over n squared. A sub n plus 1 excuse me, it's going to be 2 to the n plus 1 over n plus 1 quantity squared. So we look at the limit as n goes to infinity of this ratio, 2 to the n plus 1 divided by n plus 1 squared. That's a sub n plus 1 divided by a sub n. In this case, we do take the reciprocal of the denominator to make this into a multiplication problem. So we get that. So what do we do? Well, again, the exponential ones we can simplify. 2 to the n plus 1 divided by 2 to the n is just 2 to the first power. So just get 2. And the second part is n squared over n plus 1 squared. Now if I take the limit as n goes to infinity, this doesn't change. Here, basically, I have n squared over n squared. And then I have 2n plus 1. So if you multiply this out, you get n squared plus 2n plus 1. So it's a ratio of two polynomials which have the same highest order term degree, so you take the ratio of leading coefficients. So this part will become 1. So we get 1 times just the number 2. The answer is 2. So since the limit as n goes to infinity of the absolute value of the ratio of a sub n plus 1 over a sub n equals 2, which is greater than 1, the series diverges. So if I go back to this original thing, how can I make this end up being less than 1? Well, if I, instead of raising 2 to the n power, if I did a half raised to the n power, just any number here would, any number between 0 and 1 would make that work. Okay, so that's 19. It says series diverges. Okay. Okay, let's do the 2 remaining in this part. So I have 22. So we actually have a alternating series here. So because of that, I'm trying to see if we've done this one similar. We did a similar. 19 is similar to this, except that we have this alternating part. So we don't actually have to use, well, it says use the ratio test, so I guess we can do that. Yeah, you could also use the problem with using the alternating series test is you have to do this inequality and prove that this is true, and it might not be very obvious what's going on, so we can use the ratio test. So a sub n is -1 to the n minus 1, 3/2 to the n divided by n squared. So a sub n plus 1 is going to be negative 1 to the n plus 1 minus 1 times 3 halves to the n plus 1 divided by n plus 1 quantity squared. Now, the negative parts you can just ignore, because what we do is we take the absolute value of the ratio. So all the ones that involve this alternating 1 plus and minus 1, it just doesn't, you don't have to worry about it. We'll still put the absolute value here, but we can drop the 1 parts. Okay, so we have a sub n plus 1 divided by a sub n, like that. So we can take the reciprocal of the denominator, which I haven't done yet. First I got to write the numerator. So we take the reciprocal of the denominator. Okay. Simplify it. So we get 3 halves to the n plus 1 divided by 3 halves to the n. So that's just going to leave us with 3 halves. And then we have this ratio. We had the same one before, and what we did was you can multiply this out. But the highest order terms are n squared and n squared, so this is going to become 1 when n goes to infinity, because you're going to have infinity plus 1, which is basically infinity. So you get infinity over infinity, so that's 1. Okay. So the answer is 3 halves, which is, again, greater than 1, so this is going to diverge. So the series summation from n equals 1 to infinity of 3 halves to the n. Actually, we have the negative 1 thing in there. What this is saying is that even without this alternating series, that the original one would also converge. So if I didn't have an alternating series, it wouldn't converge. Actually, both of them wouldn't converge. So in this case, the key thing is that even the alternating series doesn't converge. And the alternating series, I think maybe also this may not go to 0 as n goes to infinity. That may be the other issue. I'm not exactly sure. But anyway, using the ratio test, because this result, the limit as n goes to infinity of this ratio is 3 halves, which is greater than 1. You look on your sheet, ratio test. If the limit is greater than 1, then you go up to the top, it says it diverges. And that's what you write down. Okay, so that was 22. Got one more here. We'll quit. 25. Actually, we'll do the next one. We'll do 33 as well, because that's a short one, and it is still talking about the ratio test. So 25 is summation from n equals 0 to infinity of 4 to the n over n factorial. So a sub n is 4 to the n over n factorial. A sub n plus 1 is 4 to the n plus 1 over n plus 1 factorial. So we do the limit of the ratio of these two. So we have 4 to the n plus 1. We have a sub n plus 1 divided by a sub n. Can we get a form where we can do some simplification? So I take this, take the reciprocal, multiply it by it. So the simplification, we got the two kinds that we know how to do. This is going to be 4 to the first power, and we divide by n plus 1. That's because n plus 1 factorial is n plus 1 times n factorial. N factorials cancel out, we're just left with n plus 1. And then here, 4 to the n plus 1 minus n, using the properties of exponents, the n's cancel out. And the answer is 0. So that's because 4 divided by infinity is 0. So it's 0. So since the limits as n goes to infinity of the ratio of a sub n plus 1 divided by a sub n equals 0, which is less than 1, the series converges. And we check our answer, and it's correct. Okay, so we have 2 new tests. Okay, one more, this group, and the question is 33. So it shows if you use the ratio test to prove the p-series test results. It says verify the ratio test is inconclusive for the p-series. Okay, so we can't use it. So that's so when it means inconclusive, it just means we don't know. That this test does not tell us whether it works. You have to actually use another test, which is the p-series test. So you can't use every test to prove this is anything. It doesn't work all the time. There's some cases where it's inconclusive, and that's when you have to use a different test. So a sub n is just 1 over n to the 3 halves. A sub n plus 1 is 1 over n plus 1 to the 3 halves. So we take the limit as n goes to infinity of the ratio 1 over n plus 1 to the 3 halves divided by 1 over n to the 3 halves. So you take the reciprocal, so what we're going to get is n to the 3 halves divided by n plus 1 to the 3 halves. So what's going to happen here? Well, if you let any positive number raised to an exponent greater than 1, you're going to end up with the numerator being no. So, yeah, I mean, when n goes to infinity, the two terms in the numerator and denominator are essentially the same thing, because you're going to have infinity plus 1, but that's basically infinity. So you get infinity 3 halves over infinity 3 halves, which is equal to 1. So that becomes equal to 1. And if you go to your sheet for the ratio test, it says, comment, the test is inconclusive if the absolute value of this ratio is 1, which is what it is. So that's inconclusive, so we can't prove it's either convergent or divergent based on the ratio test. You actually have to use the p-series test. And in this case, since p is greater than 1, this does converge. Okay, the next group are using the ratio test, but the root test. And it's a pretty simple test, and we use it when you have a series where you have the whole thing raised to the n power. So here's an example. Slash 4, all examples. So I have n over 2n plus 1 raised to the n power. So notice all of this is raised to the n power. And so really all I have to do is have this ratio be less than 1 as n goes to infinity, and it works out. So the root test, what we do is we take the limit as n goes to infinity of the nth root of this thing raised to the nth power. So what that does is basically...
Okay, so we have two new tests. We're looking
inside
at
power
convergence of infinite series.
over 2n.
The first one is the direct comparison test.
And what you're going to get is 1/2.
So we have a couple problems here that involve the direct comparison
We've
test.
got
Well,
2n to the
see
first
what
power.
that is.
and
Here's
first
the
power.
second.
So
We
it's
take the ratio of leading coefficients. Get the
1
x
and
in.
2.
Get a half. So then we go look at the rules.
And the rule says for a root test.
So that's our infinite series. And what you want to do when using direct comparison test, you can come up with a function
which it
that is
is
always less
is less than
than
1.
this, or always greater than
Therefore,
this. And if that one converges, then you get it. So a lot of times you have these situations where you have some kind of function plus a constant. And so if you get rid of the constant, so this would be the series a sub n is this, and this would be the series b
Now if
sub
I
n.
had 2n over n plus 1, then it wouldn't converge because I'd have a limit of 2 instead of 1/2.
Because this number, whatever you get here, it's going to be positive anyway.
Third problem.
It's positive. So when you add 2, this is going to be a slightly larger number than that number.
Put you guys at
And as a consequence,
Okay,
this 40, you can always say that a sub n is always less than b sub n of 4n plus 3 over 2n minus 1. And because of that, you can use the direct comparison power, which basically says now,
root test.
if
So I look at
this converges, then this converges.
goes to infinity.
So something bigger converges and something smaller has to converge as well.
Of
At this point, you can use any of the tests that we have already used. So this is one of these. I think it's the p
n
test.
power. So this is the root's 1 over n.
Correctly. So if you go
1 over
back
n
to
times
page
some
619,
base
you
to
see
the
that
n
1 over
times
n to the
same
p.
base to the 1
So
over n.
p in this case is 2.
Just the term. So
Using the p
limit
test,
as n goes to infinity of 4n plus 3 over 2n minus 1,
what we have
which is equal to 2.
is
Ratio of leading coefficients.
p is equal to 2,
which is
and
greater than 1.
what
Therefore,
we found out, what we know is that if p is
from the
greater
root
than 1,
test,
then it converges. So in this case, p is greater than 1, so 2 is greater than 1. Therefore, the infinite series b sub n converges. So use the p-test to do this function, and then as a consequence,
equals 1 to
infinity of
using
the nth root
the n plus
direct
1
comparison
raised
test.
to the nth power.
Interesting. Okay, so again, what we do is we take the limit as n goes to infinity of the nth
Also
root of 2, and I think I'll be saying that in some of the, let's group all that together so I don't have to write it out.
So there's
Okay.
so the nth root. So
Since this converges because this is always greater than
Well,
that.
this is the fire pit. We've spent, it's now 3 o'clock, we've got about an hour of light left. We're going to be cooking up one more bit of food before the rest of the day to end the day, really. This has taken all
what's
day
gonna
to
happen
do this,
here?
and yesterday. So we've got,
So,
this is all
well,
clay.
we have to actually,
When we dug down, if you remember yesterday, we dug right down here. We were digging up loads of clay. We stored that clay in a pile just to the side of the shelter. And now we've used that clay again to basically
so we'll call that
completing and to kind of cement down the outside stones here. So
again, if we get rid of the 1,
we're not sure, we've not done loads of clay work before,
now,
so
the limit of this
mix
is
it
going
with,
to be
like straw and things like that to make a
equal
kind of cob. You
1.
can mix it with ash
So
for
that
the
puts
fire,
it right at the
but we haven't done that
inconclusive
for this.
thing.
We're just kind of going with the flow here
So
and trying to save a little bit of time where we can.
we get that.
So we're
Now,
not
what
going to have a
does
fire
have
in
to
this
use
today.
to do
Because
that?
we're
Well,
gonna try and let it
because
dry
this
naturally,
is
and then perhaps in a week's
so
time
what you have to use is
start
one
some
of those
small
low
fires in
voltage
here, a couple of small
problems.
fires,
So that's
just to let
when
that
you
dry
have
out
N is
over time and dry slowly. So obviously clay does
to the end
crack
anyway,
when it
so
dries really fast. But
because we have
essentially
1
this
in
is
the
the
numerator,
pit.
next
It's a pit. It's a big pit. We reckon it's about easily 4 foot by 2 feet.
1 to any
And
power
then the reason
one.
we put slabs on the
So
side here as well
consequences
is
of
that
geometric,
these
we take
will
the natural
eventually, you'll
log
be
of
able to
both
walk on
sides.
the side of these.
Save it.
And it also means if we've got hot pots and pans and things like that, we can
then
place
take
them
the
on the side
exponent out.
anywhere around the shelter, around the fire pit, sorry. We've got one more big huge stone to put at the back here. But yeah, other than that, it's finished. But you can see why we've left that roof open now, just because the light that it allows in for the filming, and also it just gives us more room to manoeuvre and carry things without having to crouch down. So, hope you're enjoying it so far, guys. We are. Let me show you close up.
So here we're going close up. You can see we've done the pointing as best we can.
When you do that,
around there,
you get
it's all wet at the moment, so hopefully that will set over time.
take the limits
But it's
of
bang
this.
smack in the centre of the shelter,
I think that's the
near the
one.
door, just so that if any cold draft comes in through the entrance, this fire will keep that
Page
cold draft away.
30608.
The idea is to have maybe a
So
few
we have
benches
A,
here,
which
and a
is
bench
keyed
there,
in and determine
and then at the
result
back, across there, and along
R.
here to
So
have
we're
some
using
raised
this
beds.
thing.
Let us know your
So
thoughts
what we do is
on
we
that.
use Lovecott's
This is
rule.
as far as we've
Make
got
sure
today.
that this limit is
We're
on
getting
the
rest.
convergence
It's taken
limit
a
of
long
R
time
is
using
the
clay.
limit of the
Very
ratio.
long time,
So
but
you go 1
it's
over
a very
n
rewarding job
inside
doing
this.
this.
So the
Yeah,
absolute
the
value
idea,
of
we've got
R
some
is
stones here, we're going to put a
21,
big old
0,
slab
so
stone
it
there,
converges
which we
R
found in the woods
is
earlier.
in this
And
range,
that's going
and
to be when we can
since
put our
here
pots
I
and
got
pans and things like that.
since here I
This will
get
all be, when it's
1
dry,
R,
we'll be able to walk on all
equals
these
1/3.
with the ease of the shelter.
So
Come right
that's
down.
We are going to
then
finish
what
off
you
the
do
day.
is then you take the e to the x again. So you take e to the limit as n goes to infinity of the natural log of y is equal to 0. So you do that, and you get e to the 0, which is 1. So what we find out is that the limit of this whole thing is 1 once you solve for it. Okay, so that equals 1.
Okay.
So you get 2 times 1, which is 2.
We could separately.
And 2 plus 1, so I
Multiply
think you get
x
3.
squared
The
by
answer is
2x
3 here.
Plus
And
4.
since 3 is greater than 1, it diverges.
And end up with a third order. 3 times negative 1.
Okay, obviously I'm not going to give you one that hard, but
we-
you can kind of see how it works.
3 plus 2 is
And now I'll
equal to
check to
1.
see if actually I did it right.
X squared
That's
plus
problem
4.
43.
1/5. Near
So,
factor
okay,
of
what we
quadratic.
do is
And
do
so we
that,
repeat quadratic factor.
and just take the limit. So that's, we get 0.
So there you go.
The natural log of 0 is
Shorted.
we get 1. So the answer is 3. And since, yeah, that's exactly right. And then the final one is 46, I guess. 47. I'm not sure why I didn't do 46. Maybe that's a sign that. 47. So I'll get the summation from n equals 1 to infinity of 1 over n minus 1 over n squared to the nth power. So what we do is we take the limit as n goes to infinity of this thing to the nth root. So here's the nth root of 1 over n minus 1 over n squared to the n power.
Okay, so this is Monday.
And so the exponent disappears. So what I'm left with is 1 over n minus 1 over n squared. And so you'll get 0 minus 0, which is 0. 1 over infinity and minus 1 over infinity squared, so that becomes 0. So since 0 is less than 1 by the ratio, the root test, series converges.
So I'm going to do one more of these.
Did I say root test earlier? Root test, yeah, okay, dude. How about this one? Root test, okay.
So
Ratio test. Okay, so it says 47 converges. Yes, exactly. Okay, that's it for that section.